Hi, grade 11 to 12. Welcome back once again to this session. We are still continuing with Euclidean geometry, but in this session, we'll be focusing on applying the theorems, mainly focusing on proofs. How can you use this theorem to prove something? Okay, so we're just going to start with this question. So you are given that BD is a tangent to a circle. We can see our BD is a tangent there. With the center O, right? And we are also given what? We are also given that BO, our BO is perpendicular to AD. We can see by that 90 degrees there, right? Then our first proof is that, let us now prove that CFOE, where is CFOE? CFOE, this quadrilateral here. Let us prove that is a what? Is a cyclic quadrilateral. Okay, so in the other session we showed you three ways in which you can prove if a quadrilateral is cyclic, right? Number one, we said if you see like oxbow, something like that, if you manage to prove that this angle is the same as this, or rather this angle is the same as this, then you deduce actually is a cyclic quadrilateral by converse angles in the same segment, right? If you just have a quadrilateral like this, if you manage to prove that this angle plus this angle is 180, then you can also deduce it's a cyclic quadrilateral, or rather this angle plus this angle is 180, then you can deduce, right? Or rather, if you can manage to prove that an exterior angle is equals to opposite interior angle, you can also deduce that is a cyclic quad. So very, very important, we must check what kind of cyclic quad is this, right? Then we can be able to go and prove. We can see that in this cyclic quad there's an exterior angle here, right? Okay, let me just delete those red lines. So this is our cyclic, our quadrilateral. We can see there's an exterior angle of 90 degrees, right? So if we manage to prove that that angle is equals to this angle here, we can conclude that it's a cyclic quad, because exterior angle will be equal to the opposite interior angle. So it's the converse exterior angle of a cyclic quad. Okay, so we can do that, or someone can prove that actually when you add this angle plus this angle is 180, then you use converse angles or opposite angles of cyclic quad as supplementary. Okay, so either way. Okay, so how are we gonna prove? So I'm just gonna use an exterior angle because I can see I've already been given an exterior angle in that cyclic quad. Or rather, let me highlight this quad that I'm talking about, is this one. There's an exterior angle of 90 degrees, right? Meaning that we have a angle OF is equals to what? Is equals to 90 degrees. By what? That angle is just given, right? We are given that angle. Okay, what do we know about this angle here? Look at this diameter here, AE. We know that the angle subtended by the diameter at the circumference is a what? Is a right angle. Can you see? It's quite simple. So meaning that we can say A angle CE is equals to what? 90 degrees. By what? Angle in what? In semicircle. Okay, angle in semicircle. So we know that that one is 90 degrees by angle in semicircle. Can you see now? We can now conclude that therefore our exterior angle, angle AOF, is actually equals to the opposite interior angle, which is ACE. Because what? Both of them are equals to what? 90 degrees. Therefore we can conclude that actually CFOE is a what? Is a cyclic quad. Okay, CFOE is actually a cyclic quad. Why are we saying it's a cyclic quad? By converse exterior angle, right? Converse exterior what? Angle. Converse exterior angle theorem. We know that if an exterior angle is equals to opposite interior angle, we can deduce actually there's a circle within that quad, right? In other words, it's a cyclic quad. Okay, let's now go to number 2. So in number 2, they want you to prove that line FB is actually equals to line BC. In other words, they want you to prove that FB, this one, is equals to what? To BC. Prove that this one is equals to this. The question is, if FB is equals to BC, how will we know that they're equal? By actually proving that this angle is equals to this, right? If we prove that the base angles are equal, we can deduce that actually this one is also equals to this, right? By what? Converse properties of isosceles triangle, right? Or rather, someone can say angles opposite equal what? Equal sides, right? Because we have proven that the angles are equal. Angles that are opposite, they are equal because of equal sides. Or rather, someone can say sides opposite equal angles opposite. Okay, so you can give that reason. But we know that base angle of an isosceles triangle, if base angles are equal, then also the lines are equal. So in other words, to prove that this line is the same as this one, we have to prove that actually this angle here is equals to angle what? Is equals to that angle. Okay, so that's what we have to prove. So let me just write what we are required to prove. If we manage to prove that angle BFC is the same as angle BCF, then we can actually conclude that the lines are equal. All right. How are we gonna prove this? Let's go and check what these angles are equals to, right? We're just gonna start with this one, angle BCF. Can you see that this is a tangent, right? And this is the angle between a tangent and a what? And a chord, right? And a chord. What does it say? The theorem says the angle between the tangent and the chord is equals to the angle subtended by the two other chords. Let me just show you the two other chords in yellow in the circumference. Can you see? Meaning that we can deduce that our angle CBCF is actually equals to angle AE what? AEC. By what? By tan chord theorem. Okay, by tan chord theorem. All right, let's go and check now what this other angle is equals to, right? Look at this. We've just proven that this thing is a what? Is a cyclic quad, right? We've just proven that this is a cyclic quad. Can you see? We've proven that this is a cyclic quad, meaning that if this is a cyclic quad, this is an exterior angle. We know that exterior angle is equals to opposite what? Interior angle. Okay, so we can deduce that, but B angle CF is also the same as what? As A angle EC, right? By what? By exterior angle of what? Of cyclic quad. Remember, we just proven that it's a cyclic quad, meaning we can apply the properties of cyclic quad in that thing. Okay, can you see now that both these angles are equals to the same angle? Both of them, they're equals to angle what? Angle E, meaning that we can equate them to say B angle CF is actually the same as B angle FC. Why? Because both of them are equals to A angle EC, right? We've just proven that, oh, actually, these two angles are equal because both of them are both equals to angle what? Angle A and EC, right? So if these base angles are equal, we can deduce that therefore FB is actually equals to what? To BC, right? FB is actually equals to what? To BC. By what? Angles opposite equal what? Equal sides. Angles that are opposite are equal because of equal sides, right? Or rather, because now this is side, we can start with angles, right? Because we are equating sides. Rather, we can say what? Sides opposite equal what? Equal angles. Very, very important. So when you are equating sides, you start with sides, right? Because it's the sides that are equal because of what? Because of equal angles. We have just proven that the angles are equal. Then we can deduce sides that are opposite are equal because of equal angles. So that's our reason. Okay. Let's now go to number 3. Very interesting question. They want you to prove that angle AOC is this angle here in is it yellow orange? I think it's orange. Angle AOC is the same as 2 times angle BFC. So it's the same as this times 2. Okay, they want you to prove that. How can we prove that? So what you do is you use your properties of angle at the center, right? You use those properties. We know that angle AOC is an angle at the center, right? What do we know about angle at the center? Remember theorem number 2? Angle at the center of the circle is actually the same as 2 times angle subtended at the what? At the circumference. Okay, meaning that our angle AOC is the same as 2 times angle what? Angle AEC. Right. By what? Angle at what? At center is same as 2 times angle at what? At circumference. Okay, so that's what we know, right? Our angle AOC is the same as 2 times angle AEC. But we know something very, very important here. Look at this, very interesting. But this angle AEC, right, in yellow, this one, is actually the same as angle BFC, right? By what? Exterior angle of a cyclic quad. Remember, we've proven that this is a cyclic quadrilateral, meaning BFC is an exterior angle and is equals to opposite interior angle. Can you see? So we can deduce that, but our angle AEC is the same as angle what? BFC. By what? Exterior angle of what? Of cyclic quad, right? Because we have proven that that thing is a cyclic quad. Very, very important, right? Meaning that we can replace now our AEC by what? BFC. Then we have proven that our angle AOC is the same as 2 times angle BFC, right? So where there is AEC, because it's equals to BFC, we just replace by that and you would have proven that. All right. I want you to they're asking you if a DC will be a tangent to a circle passing through CFOE, right? We have our CFOE, right? They want you to prove whether DC is gonna be a tangent or not, and you have to motivate your answer. Remember, we've just proven that a CFOE is a cyclic quad, right? But that does not automatically imply that this is a tangent. If this is a tangent, what do we know, right? Remember, we also focused on how you can use the converse tan chord theorem to prove that a line is a tangent, right? And how do we do that? So if really DC is a tangent in this circle passing through CFOE, meaning we have a circle here because we have actually proven that it's a cyclic quad, then we have to find that this angle here, right, this angle between this line, which is assumed to be a tangent, and a chord must be equals to the angle in the other segment that is subtended by the 2 other chords. In other words, if this is a tangent, then we have to prove that indeed our DCE will be the same as COE, right? If we manage to prove that that angle is actually the same as that one, we can deduce that, oh, actually DC is a what? Is a tangent by what? By converse tan chord theorem, right? So let's go and try to prove. If we fail to prove that, if we find that this is not the same as this, we'll automatically say actually it's not a tangent, because this equation is saying will DC be a tangent? It means there's a possibility it cannot be a tangent if these are not equal, but if they're equal, obviously it's a tangent. Okay, so we're just gonna go and calculate what does this angle equals to. What does this angle equals to and what does this angle equals to? If they are equal to the same angles, then we'll automatically say actually they are equal because both of them are equal to the same angle. So our duty now is to go and calculate this angle D, angle CE, and we check what does it equal to, right? So this angle here, if you check a bigger circle, right, I mean this circle with center O, we know that this line is a tangent because we have been given that BD is a tangent, right? If BD is a tangent, meaning that this is a chord and this is a tangent, angle between chord and tangent is equal to angle subtended by the two other what? By the two other chords on the circumference, meaning that our D angle CE will be the same as what? At C angle AE. By what? By tan chord theorem, right? Okay, we've just calculated what this angle is equal to, this one, the angle CE. Let's now go and calculate what our angle C angle OE is equal to, right? Let's go and check for that. Okay, so let's check. C angle OE is an angle at the what? At the center. Can you see? C angle OE is the angle at the center. We have this angle at the center. We know that angle at the center is 2 times angle subtended by the same arc or chord at the what? At the circumference. Okay, meaning that we can deduce that C angle OE is actually 2 times angle at the circumference, which is what? Which is C angle AE, right? By what? Angle at what? At center is equal to 2 times angle at what? At circumference. Okay, can you see now? We've just calculated the angle CE and C angle OE. Can you see that these two angles are not equal to the same angle? This one is just equals to C angle AE. This one is equals to 2 times C angle AE is double that one. Meaning that we can deduce that actually, therefore, D angle CE is actually not the same as what? As C angle OE. What does this mean? Okay, it means that this angle here, we are saying this one is not the same as that one, right? Because they are both equals to 2 different angles. This one is equals to C angle AE. This one is equals to 2 times C angle AE. Meaning these angles are not equal because they are not equal to the same angle. And what does it imply? If this angle is not equals to this, then it means that although here we have a circle and we have just proven that it's a cyclic quad, meaning that our DC is not what? Is not a tangent. DC is not a tangent to a circle passing through what? Passing through CFOE, right? It's not a tangent, right? And why are we saying it's not a tangent? Because it does not obey converse tan chord theorem, which actually says angle between a line and a chord is actually equals to the angle subtended by the two other chords on the circumference. We are saying that they are not equal, right? Meaning that DC is not a tangent, but if they were equal, we were going to conclude that actually DC is a what? Is a tangent. But in this case, they're equal to 2 different angles, meaning these two are not equal, meaning DC is not a what? Is not a tangent. And our reason for that is because it's not applicable to what? Not applicable to converse tan chord theorem, right? Not applicable to converse tan chord theorem. So this was a little bit tricky, but I hope you now get the point. All right, grade 11 to 12, thank you very much for watching. Thank you very much for joining this session. I hope you learned something new. If you're new to this channel, make sure you have subscribed and hit our notification bell so that you may be notified every time we upload a new video. Otherwise, in this session, we were focusing on applying the theorem and